Exercise 17. Suppose w equals f of x, y, z equaling 2x plus 3y minus c, where x, y, z lie in S. The minimum value of w is sought. The graph of f would require 4 dimensions, so it cannot be provided. However, the graph of its domain, feasible region, S, is provided. S is the solid triangular prism illustrated, and S contains its boundary surface. Working manually, calculate the minimum value of w. Okay, on our previous exercise, when we were determining whether or not a function was a linear programming question, we decided that this is a linear programming question. Reason being that, first of all, we are finding a minimum value of w. That's an optimization question. W, with this formulation, is a linear function. The domain of this function here is drawn in this picture, and from this picture you can actually see that it is a convex region, and it contains all its boundaries. So this could all be described by a system of linear inequalities, each of which would be a greater than or equal to, or less than or equal to variety, and that qualifies this for linear programming. That being the case, we have a theorem that says if the feasible region is non-empty and bounded, which it is here, there's something here, so it's not empty, it's bounded, because you could enclose this solid with something bigger, then we know that the maximum and minimum, for that matter, will occur, and they will occur at a vertex. The maximum at one vertex, the minimum at some other vertex perhaps. And so our strategy will be to calculate w at each vertex, and from that we will expose just what the minimum value is. So let's get started with some tabulation. Okay, so here we're going to have the vertex here, and over here we'll calculate w equals 2x plus 3y minus z. Okay, well, let's see, maybe we start at the base, this rectangular base here, and we could have 5, 3, 3 to consider. Let's say 5, 1, 3. 3, 1, 3. 3, 3, 3. 2 other points here. 5, 1, 6. 3, 1, 6. Okay, computation, here we go. 2x, that's 10. 3y, 3 by 3, 9, minus z, 3. Looks like 19 minus 16. Next vertex, 2x, 10, plus 3 times 1, minus 3. Net effect, 10. Next vertex, 2x is 6. 3y would be 3. Minus z is minus 3. The net effect there, 6. Next vertex, 2x is 6. 3y would be 9. Minus z is minus 3. The net effect here, let's see, 15 minus 3, 12. Next vertex, 2x is 10. 3 by 1 for 3y, minus 6 for minusing z. We're up to 13 minus 6. Looks like we're at 7. Okay, last vertex. 2x, 6. 3y, 3. Minus z, minus 6. Net effect looks like 3. Okay, we are seeking the minimum value of W right here, it looks like. Okay, our conclusive statement. The minimum value of W is 3. That actually answers the question. Go one step further though. This occurs at x, y, z equaling 3, 1, 6. About the only check you could do here would be to review the arithmetic, look for an arithmetic error. Otherwise, the basic principles are pretty straightforward. And looks like we are all done here. Exercise 19. Consider the following problem. Determine the maximum value of z, where z equals y plus 2x, subject to x minus 4y less than or equal to negative 2, x plus y less than or equal to 8, and 4x minus y greater than or equal to 7. Part A. Is this a linear programming problem? Explain the basis of your conclusion. Alright, let's look this over. This problem, as we are looking for a maximum value of z, okay, this puts it into the realm of optimization. Alright, we need to have that going on. This z is a function defined with z equals y plus 2x. That's a linear function. Okay, so it has the other requirement now. Let's look at the domain of this function. What kind of conditions are restricting or constraining the x's and y's? It has these inequalities here that are defining the domain. This one is linear. The second one, x plus y less than or equal to 8, that's linear. This third one, also linear. Okay, it's got a domain defined by linear constraints. And if we look over the types of inequalities here, less than or equals 2, less than or equals 2, greater than or equals 2. Alright, those are all amongst the permissible types of constraints that a linear program can have. You could also have an equals to case in here too. That would be allowable. Alright, so ready to make a conclusion for this part A, that we believe it is, yes indeed, a linear programming problem. And let's write down all that we've discussed into a summary sentence. Okay, we record our answer for part A. Now, let's go to part B. If this is a linear programming problem, then solve it manually. Alright, well, we first need to sort out what this domain actually is so that we can find the vertices of this domain. That's going to be the important first part. Let's get started with that. In graphing these inequalities here, we'll need some boundary lines initially, and then choose which side of the line to shade, and look for the overall common intersection. Okay, now what kind of coordinate system may work here? And with a system, it's really hard to predict too much. As far as if we were to graph intercepts of the corresponding equalities here, it looks like the kind of numbers we need are not especially large, maybe as much as 8, -7, this sort of thing. Okay, let's start off with a pretty simple coordinate system. Okay, I'll make it scaled at 2 units per centimeter. 4, 8. 4, 8, -4, negative 8, negative 4, negative 8. Labeling the axes, we'll make this x's, this will be y's. Alright, let's go to that first inequality here. We can call its boundary line L1. That's what we can be working on for right now. And this means the corresponding equality, that is the x minus the 4y equaling negative 2. Alright, let's choose to graph this in blue, light blue. We can get the intercepts here pretty easily if we let y be 0. X is negative 2. There. If we let x be 0, y would become positive 1/2. Alright, so 2, 1 is there, 1/2 is there. Okay, when we get a couple points that are so close together, I like to get a little more accuracy in the lines, so I think I will choose something out here. What if we let x equal to 8, for instance? What's that mean? That would give us negative 4y equaling, alright, subtract 8 from both sides, negative 10, which leads to then y equaling a positive 10/4, positive 5/2 in other words. Okay, that would be a little better. So out here where x is 8, now 5/2, that is actually 1 1/4 centimeters. Okay. There. Alright. Take the x-intercept and that point to create the straight line, the boundary line, and this is a solid line because the inequality is a or equals to type. Okay, label this with its boundary line equation. This was x minus 4y equaling negative 2. Okay. Next, second inequality. Here it is. Let's get its boundary line. Call it L2. Boundary line of the second inequality, meaning x plus y equaling 8. Okay, this one's pretty easy to graph because the intercepts are quickly calculated. Let x be 0, y is 8. If y is 0, x is 8. Okay, there, there. Oh, we're getting a little ahead of ourselves. Hang on. Back to this first inequality. Sure, we graphed the boundary line, but what about which side to shade? Okay, back up to here for a minute. Let's test 0, 0 into this inequality and see what happens. Alright, if we put 0 for x and 0 for y, that leads to the statement 0 less than or equal to negative 2, which is false. Okay, so this means we don't shade 0, 0 side of the line, it's the other side of the line. Alright, so that would be up here. Just a light pencil shading because I'm waiting for the intersection to develop before I pull out the dark color highlighter to do the shading of the region R. Okay, now back to our second inequality, whose boundary line has 2 points ready for us to connect. To label its equation, this is x plus y equaling 8. Now, which side of the line gets the shading here? Substituting 0, 0 into this inequality would give us 0 less than 8. That's true. Alright, so that means we should shade 0, 0 side of the line. Alright, now we start thinking of the intersection as well. So far we have an intersection developing in here, kind of within this angle region that we seem to have developing. Okay, ready to go to the third inequality. Let's get its boundary line, L3, for this third inequality boundary line. That means we need to graph the solutions of 4x minus 7 equal 4x minus y equaling 7. Okay, let's see. Let's choose to go with the color green. If x is 0, y is negative 7. Okay, -4, -6, -7 right there. If y is 0, x will be 7/4, 1 3/4. Okay, be a little careful here. There's 0 and 2, 1 3/4. Halfway would be 1. We need to do 3/4 of this distance here, about there. And sketch the line, which is solid because it's an or equals to type of inequality we are graphing. Okay, we can label the equation that goes with this. This is 4x minus y equaling 7. Now, which side of the line gets the shading? Testing 0, 0 into this inequality would give us 0 greater than or equal to 7. That's a false statement. So, not 0, 0 side of the line, but rather the other side of the line. Okay, we had an intersection developing in this angle. Now we're to the other side of the line from 0, 0. This means the overall intersection is now in here. Let's give this the sort of permanent shading here. Okay, now this here, purple. Okay, we're calling this R. That's the domain of the function. And in the world of linear programming, domain is usually called the feasible region. Now, one of the more important parts of this feasible region, of course, are the vertices. We seem to see 3 of them here. It's a triangular region. Okay, so I'm going to emphasize these vertices here. Second one there. Third one there. Alright, now we need to get these calculated. Let's start here, and now we can kind of organize our solution here. We're doing a vertex calculation. Alright, now this one is the blue line and the green line. The blue, x minus 4y equals -2. And the green line, 4x minus y equals 7. Okay, let's see. This is more or less ready for some elimination. What could we do? Perhaps we choose to eliminate the x's. So it'll be the bottom equation minus 4 the first. Okay, so 4x minus 4x. X's are eliminated. Here, the negative y, subtract 4 of these. That means add 16y. -1 and add 16. That gives us 15y. 7 minus 4 times -2. That means 7 plus 8. Okay, and this leads to a y equaling 1. What's our check here? Look for graphic consistency. Over here, does this look like a point whose y is 1? Remember, it's 2 units per tick mark, so this is 1 for y. This is looking good. Keep going. Okay, we could use the first equation as an easy source for x. X would equal, we'll have the -2 and add 4y. -2 plus 4 times 1, and that gives us 2. Look for graphic consistency. X being 2, yeah, it looks about right. So we can label this with its coordinates. This will be 2, 1. Okay, now let's come over here. This vertex. This is the intersection of the green line and the red line. The green line has the equation 4x minus y equals 7. The red line is x plus y equals 8. Okay, this is already easily ready for some elimination method. Add the equations together, we'll eliminate the y's. This gives 5x equals 15. And this will lead to an x equals 15 over 5 is known as 3. Does that look consistent with the graph over here? There's the point. 2, 4. Yeah, 3 around in there. Looks fine. Keep going. Y can be obtained from using this second equation. X is now known to be 3, so y could equal 8 minus 3, known as 5. Does that look graphically consistent? Here we are up here, 4, 6, 5 in there. Yeah, looks pretty good. Alright, we're confident to label this as the point 3, 5. Okay, something else right here. This is the intersection of the red line and the blue. Okay, so now we concern ourselves with an intersection of x minus 4y equals negative 2, and red line, x plus y equals 8. Okay, this is ready for some elimination method. We could take first equation, subtract the second. X minus x. X's are eliminated. Negative 4y, subtract y. Negative 5y. Negative 2, subtract 8. Negative 10. Leads to y equals negative 10 over negative 5, positive 2. Does that look right? Back up here. The y is about 2. Yeah, keep going. We could use the easy second equation as a source for x now. X would equal 8 minus y, which is now known to be 2. That gives us 6. Does that look okay? Yeah, this x out here looks pretty much like exactly 6. Okay, ready to label the vertex here with the coordinates 6, 2. Okay, before we keep going, we really should do one more check here, and this region could have been misgraphed. So I really like to check that region right here. What could we do? Let's locate a point that is it's clearly in the region that we've graphed here, and test it out in all of the original inequalities to see if it's really working. Now if we come in the middle here, let's see what kind of point is more or less in the middle of the region, so there's no doubt about it being here. Alright, I'm thinking about coming up 1.5 centimeters. That would be a y of 3. And coming across 2 centimeters. Okay, that would be an x of 4. So I think surely 4, 3 is in our graphed region here. 4, 3 is in R. And so now let's test matters out. Let's substitute this point into all of the original 3 inequalities and see what the verdict is. In the first one, we have got x minus 4y. That would be 4 minus 4 times 3. Is that less than or equal to negative 2? Well, this is a negative 8 here, less than negative 2. True. Okay, the second inequality, which is x plus y, that means 4 plus 3. How about that being less than or equal to 8? That's 7, less than 8. True. Third inequality, 4x minus 7. Alright, 4x, 4 by 4. 16 minus the y is 3. Is that greater than or equal to 7? This is 13, greater than or equal to 7? True. Okay, you know what? The region looks pretty good. It passed this at least one test that we gave it to make sure we didn't really misgraph a line, a boundary line, or really choose the wrong side of the line to shade. It's looking pretty good. Alright, we're ready to proceed to the calculation or the determination of the maximum value of z now. We've got the domain, or the feasible region. We know its vertices, and we have our theorem that says that in the case of a non-empty, bounded, feasible set, that the function will indeed have a maximum or and a minimum value, and it will occur at a vertex. Okay, so let's go ahead and tabulate our vertex calculations of the values of z. Okay, looking back above there, let's get our vertices in order. So, vertex and z equaling y plus 2x, just looking at the original formulation of the question. Alright, we got these 3 vertices. Let's see, we have 2, 1. We have 3, 5. And we have 6, 2. Okay, let's go ahead and compute the value of z at each of these vertices. Y plus 2x. This would be 1 plus 2 by 2, known as 1 and 4. That's 5. In this case, y is 5 plus 2 by 3. That gives us 11. In this one, we would get 2 plus 2 by 6, known as 14. Alright, we seek a maximum value right here, ready to make a conclusion. The maximum value of z equals 14. This occurs when xy equals 6, 2. It's a conclusive statement. Put it in a prominent cloud so that it jumps off the paper, anyone looking at the solution. Now, we actually didn't have to mention this idea about this occurs when xy equals 6, 2, but it's good to go the extra distance and provide a very complete answer when you can. Just makes a better solution regardless. Okay, looks like we are ready to go to part C of this question, which will also give us an opportunity to kind of check over our claimed maximum value statement. Okay, part C is using calculator and or computer apps, illustrate this problem graphically. Okay, to get started, I will utilize the emulation software for a TI Nspire calculator. Okay, let's attempt to pick up the graph of this objective function, and that means since it's a real valued function of 2 variables, we need a 3D graph. So we can choose a graph application here, and let's go to the menu. Under the viewing, we go to a 3D graph. Now, what about that formulation for z? Well, let's refer back to the original problem statement where it says that z is equal to y plus 2x. Okay, so in this entry spot here, y plus 2 times x. Could push enter to see what appears here. Alright, initially we seem to have, well, what do we have here? Let's try letting this revolve and take a look. Okay, now since this is a linear function, we were expecting to see a plane in 3 space, which is indeed what we have here. Now let's consider what we would like to do about the scaling of the axes. for this issue, it's probably best to go back and take a look at domain or the feasible region again. And we see that it is entirely in the first quadrant, and it looks like the maximum x needed for this is about 6 units out, and we do want to have the y-axis appear, so that means our x is at least 0 to 6. For y's, we see that the maximum y in the domain or feasible region here looks to be about 5. Okay, and we want the x-axis, so we would want to have y's going at least from 0 to 5. A second consideration is to look at what kind of z values we've got going on here. In our tabulation, we see we have z's which were all positive numbers and out to a apparent maximum of 14. Okay. Well, since we surely want to see the xy plane, we want to make sure we have a z equal to 0 available, and to get this maximum to be appearing on the graph, we want to have a z coordinate of 14 available also. Alright, since this means the z-axis is going to be 14 units long, maybe it's best to make all the axes 14 units long, and so, and this is subjective, but I think let's go to this menu, do a couple things here. First of all, I prefer to not have the box, so I'll hide the box. Back to the menu again, working on the range zoom in the range settings. Okay, x min. Let's see, to make the x-axis 14 units long, perhaps a -7 to +7. Okay, so -7 and tab forward, +7, tab forward. Actually, since we're not putting the box on this graph, there's no need to even bother trying to put in the scaling, because this particular application does not put tick marks on the axes themselves, only on that box. So bypass that. Y-axis, okay, -7 to +7. And we'll bypass the scaling issue. The z-axis, okay, 0 tab to 14. And the other things are these angles and this distance can all be taken care of with the cursor after we get the graph to appear. So let's just click on OK and take a look at what we have here. Okay, this looks pretty good. I suppose maybe about there. You can, without changing the eye distance, by using the multiply and divide, you can sort of zoom in and zoom out a little bit. Multiply there to get us in to this level of zooming in, which looks pretty good. Last thing I think I might do is get a perhaps somewhat better resolution, it seems, by going to the computer view as opposed to the handheld view. I like the handheld view because I like to use the calculator keyboard to do most of the operations. But for this, just before capturing this image, view, computer, somehow it looks like it's a higher resolution sketch that way. Again, a subjective call. Anyway, let's go here and capture this page. Once we are captured and we store this away, we can then work on this image with Microsoft Paint perhaps to create our final product of the three-dimensional graph of this actual function. So that'll be next. Okay, here's the full graphic illustration of the problem we have just solved. It starts off by taking the TI Nspire three-dimensional graph, which had the red plane, and I looked to how we had decided to scale the axes. We chose an x-axis ranged from -7 to +7, and that enabled me to label 7 at the point there at the end of the x-axis, and the y-axis we scaled we chose to scale from -7 to +7. That gave me the information needed to put a 7 at the end of that positive y-axis. By the way, the Nspire puts the actual arrow tips beyond, just beyond the last point that you call for in the range, so that's why those 7s there are set just below the arrow tip. Also, the z-axis, it was from 0 to 14. That enabled me to label 14 as the number on the axis just below the arrowhead on the z-axis. Following that, it was time to sketch in the domain of the function, the feasible region, and for that, I just went to the domain graph and noticed that it was a triangular region with vertices 2, 1, 3, 5, and 6, 2. Okay, using the xy axis there in the three-dimensional plane, I plotted those 3 points first and then connected them with lines and shaded in the interior blue. That was the domain. Then it was time to project the domain up onto the red plane surface to get the actual function graph. Okay, so that was done by taking lines parallel to the z-axis, following them straight up, and how high to take each of those points. That's where I looked at our tabulated vertex chart and realized that the point above the 2, 1 vertex should be 5 units, the point above the 3, 5 vertex should be 11 units, and the point above the 6, 2 vertex should be 14 units above. And I used the scaling of the z-axis with that 14 unit segment to proportionally sketch the lengths of these projection lines. Then those 3 projection points are connected with green lines and the interior filled in with green. That gave the actual function, and then labeling the important maximum point there is a point in 3 space. Its full coordinates are 6, 2, 14. 14 is the z value, which is what we were seeking to answer this question. Okay, there we are, and it's all consistent with what we figured out algebraically, so this problem is really feeling right as well as having its algebraic calculation. And this graphic is a really good visualization to fully show you what is going on in a question such as this here. All right.